All the interpreted languages have to change. Today we're gonna write very simple but fast Python compiler that uses bytecode that's compiled by the CPython. We're gonna look at virtual machines. We're gonna look at interpretation, compilation. It's so fun. All right, come on, let's go. So what I've been really excited lately is compiling Python. You have a large application in Python and you want to ship it to the users. How do you do it? You compile it or package it. Nuitka takes hours to compile a simple program. Also is not making programs faster. Python also takes hours to compile a simple program. It's very hard to set up, not intuitive at all. Just like, no. So I've been making my own compiler in the background, but it's also quite a hard task. I have over-engineered it, and I did not like developing it further. But all it's doing is essentially, we have a program in Python. For example, a equals 5, b equals 7, print a plus b. What I was doing is, first of all, parsing it. So you have an assignment of a to 5, assigned b to 7, and call print with an arguments of a and b. And then, this is an essentially tree, or syntax tree. Then you lower it down to intermediate representation, which is like, you push 5, you load it, and you push 7, you load it into b, push print a, b, and call with 2 arguments. And what it's doing is the same thing that's Python doing. Python already, before it runs your program, it does all those steps, and then it executes the final bytecode. So instead of doing all this by myself, I can use the Python compiler, which compiles the Python code into Python bytecode, and then take this bytecode and compile this bytecode into C, which is so much easier. So essentially what I did is yesterday I was just like, wait, it's so fucking easy. Why don't I do that? And I just literally did it. So let's see how I've done it. It's actually so easy. I've done so much stuff is already compiling to C and is already faster than Python at least 4 times. So that's very interesting. Okay, but let's start with this program, right, that we have here. We compiled it into bytecode. What do we do next? Well, we can say, okay, we can have an array of, for example, integers. Let's say int64 type, and I have an array of them, right? Or whatever. So this will be my stack, right? And for example, I can reserve, I don't know, 2024 items in there. Okay, fine. Then when I do a push, I have a stack pointer, which will be like 0. It can be uint64t. So when I push something, all I do is I say, hey, put something in the stack at stack pointer. So you have an argument of like push, int64t arg, right? You assign to the current cell in the stack the argument, and then you say, hey, let's increase the stack pointer. That's the push. The pop, the same thing. You just get the integer in the cell and decrease the stack pointer. Okay, very easy. I can compile it to C very easily. When I push the print function, I literally push an integer of when I have, for example, my print, right? And it does some things. All I can do is just say, hey, let me cast it to an integer, and when I will be calling, the call to will pop 2 arguments and then pop a function, and it will just cast it back. So nice. Okay, that's it. It's like, I was like, yeah, okay, that's very easy. I've done that. And by the way, since I have the the simple compiler. Let's see what it will look like. Let me see. Let me show you. This will be in tiny VM. Oh, tiny or toy. Yeah, toy VM. Right. Let's see. Let's see. Boom, boom, boom. So here's our example. Let me make the code. So here we will be compiling a equals 5, b equals 7, print a plus b, which will be what? Obviously 12. And let's see what it will compile to. So I can run it. Let me show it to you. Python toy VM compiler. And I will just run it. What it will do is it will obviously use this source code, compile it with, let's see, compile, boom, boom, boom. Python has a built-in function that compiles the source code into the bytecode, which is called code object. And when the Python did all the hard work of parsing the source code, of making the bytecode, I can just say, hey, give me all the bytecode. There's a module called this, which can give you all the instructions from the compiled bytecode. Very nice. And then after I write it to a file, I literally just run clang on it and then run the compiled output. So let's see what will happen. It's writing to the file, it's compiling, and it will execute the program. Let's see. Yeah, come on, it's warming up. 12! Yes! But okay, let's see what this compiled to then. It should be in the output.c. So obviously, to support all those functions I described to you, this is the runtime of my tiny compiler. I prepend the runtime first, and then after the runtime, I have the bytecode compiled to C. Let me zoom out a little bit so you can see better. A little better. Right. So this is the runtime. Some amount of lines. And here you see, here's a stack. Here's a stack pointer. All the simple things. Push, pop, right? All right, let's see. And here is the code. So we have a global variable A, we have a global variable B, which is correct. I initialize them to 0. Then I push an int 5. I pop it, store it into variable A. I push int 7, store it into variable B. Then I push 0, which is a Python's way of supporting method calls. Doesn't really matter. Then I push the function, push the first argument, the second argument. Then I do the operation on the A plus B, right? I pop them, I add them, and push them back, and I just call them. Here are the arguments. Here's the function. That's it. Very, very, very simple. And here I, decrease them. Then I just pop them and return. Man, it's so simple. And if you look at the time to execute this compiled program, and let me make sure that when I'm compiling it has optimizations, yes. So when I'm compiling, I optimize the C code. And then, so let's see how much time it takes. Output.out. Yeah, it takes obviously there's nothing really happening there, but, it takes a little bit of time. I don't know. Little bit of time. Oh, wait, I'm sorry. That was wrong. Yeah, I don't know. If you try to run the same code in Python, I don't think we will have much of an improvement here, but just for the sake of it, just for the fun of it. 1 second. Let's run it in Python. So I have this file, tst.py, time python tst.py. It's taking much longer, but obviously it's not warm right now. Okay, now it's warmer, but it's still like, yeah, it's so much slower. It's so much slower. And do mind that I'm recording, so it's taking a toll on the performance. But like, here we're getting like, I don't know, 100 milliseconds. Here we're getting 400 milliseconds. So 4 times faster. We just compiled Python bytecode to C, made the C compiler optimize this bytecode, put it into the binary, and it works, and it compiles, it runs faster. Okay, I was like, okay, how much can I push it? What if you want to add if statements? What would happen here? Okay, let's see. If A, right? For example, if A is more than B, and then we're only printing then, or let's say less, right? Only then we print the sum. What will happen? You can literally see, it's so easy. By the way, you can use the dis module in Python, of course, directly using an import, but also you can use it through a command line. So let me show. If I open the TST again, our test file, I save it, and then I say, hey, Python, the TST py. It will print the the bytecode. So what it's doing? It's saying, hey, load a 5 into A, then load 7 into B. Yes, all correct. Then load A, load B, and compare them. Nice. This comparison will pop those two values on the stack, then push the result. And here, pop jump if false. So the result of the comparison will be popped. If it's false, we will jump to the 44. So we will just return. Otherwise, we will execute a call. Very nice. So it's very simple. All you need to do here is just look at which, look at all the instructions and see which instructions you can jump to. So for example, here we can jump only to 44. So for the 44, we will generate a label, and then here we'll use a GOTO to get to this label. So let's see what this code will compile in this simple, very, very simple compiler. Let's see. Boom, boom, boom. ToyVM compiler. It's compiling. Yes, it's 12, so it worked. But did it actually output new code? Let's see. Let's see. So we have the old code. Then we have the comparison, which pops two values, then pushes the result, compares OP less than, operation less than, pushes the value, and here we have, if the value in the stack is true that we just popped, we go to target 44. What's target 44? We just return. Oh my, it's so easy. And again, if you see how much it takes to run it, let's see, like about, well, I don't know. It really jumps all around. But let's see what about the Python version. I would assume it will be just slower. Yeah. Yeah. Well, you see, it is slower. So literally, just taking the bytecode from the program that the Python interpreter has to still compile a Python to the bytecode before it executes the file. But okay, we just, instead of taking the bytecode and putting it in the into the virtual machine to execute, why don't we take this bytecode, compile it to C, or translate it to C, and then compile it to assembly? This is just so, like, it's not much harder. Those processes are not really different, because you still have to have the bytecode compiler. Instead of implementing a virtual machine, which is so much harder to optimize and stuff, you just implement a simple compiler. And it just works, and it's so faster. I was like, okay, let's go. Let's go do something more interesting. What else can we do? I was like, okay, what if I want to not just have a integer here, but what if I want to have, for example, A can also be a string, hello, and B can also be a string, like world. What if I print A plus B? So this is not very different, but I need a way, because like, for example, if you look at the disassembly, or how do you say, by the way, very, very nice feature, if you press Ctrl R, you can reverse search through the console history, and I can just type this, and it will pop the command I last used. So nice. It does the same thing. So here, to add two numbers, it just loads them and does a binary operation. Here it does the same thing. So I cannot tell whether I'm adding two integers or two strings. How can I tell? Well, instead of storing just like a stack of integers, I will store a stack of tagged unions. So I will have a enum which says, is this an integer? Is this a string? Maybe it's a float or something else, like a function. This is the first byte or whatever, and the rest will be taken by the content itself. So either it's an integer, it will be a union, for example, of an integer, of a string pointer, character pointer, whatever. So I just have a stack of those tagged enums or whatever, and just operate on them. So you see, when I try to compile this with my little compiler, what it will spit out, obviously it will work, first of all, which is, it's nice. For the thing that was sloppily put together over like an evening, that's pretty good. But what it compiles to is, you can see, I have a val int here and val string here. So I can push the same thing, which is a value, but depending on how I initialize it, it has different things. And for example, when I do operation add, well, let me show you what val string looks like. All it's doing is it says, hey, the value is a string and the enum set to string. And you can see the definition of this thing. Very, very simple. Very simple. Union, yeah, here you have the enum. So simple. But okay, how do you add two things which you don't know, like, what are they? They can be anything. Well, if you're adding two strings, then you do this simple operation of like allocating more memory and copying the strings. When you add two floats, or like when you add something to a float, you convert the other thing to a float. For example, if you add int to float, the result will be a float. So you convert both to float. The rest is just an integer. And here the funny thing is, it doesn't check for correct types. So for example, I can literally say a funny thing. It's like, what if I add hello to 5? It's like, what will happen? In the current implementation, what will happen is, we don't have both strings, we don't have any floats, so this string pointer will be casted to an integer, this will be an integer as well, and we will add them together. Which is like an interesting, funny way to never fail. It's like your compiler or your bytecode doesn't have to fail ever. But of course, like if you know something will, will crash most likely, then you probably do want to fail explicitly. But here, it won't crash. It's just a funny way to, make it work and not check too much. So obviously the pointer is a big number. So big number plus 5 is a big number. Yeah, obviously they're different because, yeah, that's it. It's like, and another funny thing is, since I do not require any declarations of anything, I can just say, let's say a plus equals 5, and then I can print a. Since when I'm compiling, I initialize all the variables to 0. When you interpret 0 as an integer, it will still be a 0. So I don't have to actually initialize the integers. They're by default 0, which is very, very interesting and cool. And yeah, so let's see. Print a. This will output literally 5. So funny. Yeah, here we go. 5. So yeah, let me show you how I initialize it. Boom, boom, boom. Yeah, I hope yeah, it's good. It's good. 1 second. No. That was a mistake. So here we go. I initialize a variable a to 0. So the enum will be initialized to 0, which means this value is an integer, and the value itself will be initialized to 0, which means it's an integer with a value 0. So fun. So yeah, obviously if I, it also declares the variables as integers. I don't know, it's funny. Yeah. So another thing is like, okay, what if we try to do a for loop? Because like obviously we can do while loop and it will use the same jumps from an if statement. For example, while I is less than 5, let's say I plus equals 1. No, just one more time, and print I. And since I have auto declaration of integers by happy coincidence, I can just run it and it will print the numbers. But I don't need to do anything fancy to support this, because all this thing is doing is just jumping around. Edit, let's see, edit tst pi. All it's doing is jumping around. And let me see that. Let me show you to the dis. If I disassemble it, all it's doing is, okay, it compares I with 5. Obviously, it does the jump, so there's nothing special for the while. It's like all the while, the ifs are implemented with the same jumps. Yeah, you just jump, if it's less than 5, if this is false, then we end the loop, we jump to the end. If it's not less than 5, we do the, the addition and the printing. Very, very simple. And obviously in the end, you still check it. If it's still not false, you jump back to the top. Just 2 jumps and you got a loop. I can probably even draw it to you. Because it's so fun to look at how the code gets translated into, this is called graph, CFG, control flow graph, right? So let me show it to you, right? Oh, come on, load. So when you have a, oh yeah, by the way, it's a flashbang. That is, it is what it is. You got flashbanged. All right. Let's see. When you have, I don't know, a while loop, right? While or like I less than 5, you do something here. You have this I less than 5, this is where you start with. If it's false, you go, to the end after the loop. If this is not false, you go to the body of the loop, and then you jump back here. So this is the way loops work. In the Python bytecode, they have a separate I less than 5 copy pasted here, so they can do this crazy operation, but it's not necessary. You can just actually jump back to the same operation here. Still, it's like the same thing that allows you to have an if, because if I less than 5, all it's doing is it's checking, I less than 5. If it's true, do one code. If it's not true, do another code, and then they merge in the code after that. It's like you don't need anything special. But what if I want to do, and obviously it works as you see, it works, it prints the numbers. But I, for example, want to do the classic for loop, and in a Python you do it like this: for I in range of 5. How do you do that? Well, that's a little more complicated. Let's see what the bytecode looks like. So we push, obviously here we call a function. We need to call a function to get an iterator. Because, okay, let me show you. So in Python, for loop does an iteration. So if you have a iterator, which is like, let's say this is a range of 5, right? Then you need to get an iterator from it. So iterator will be iter of r. So iter is a function that will get an iterator of an object. Let's see, range iterator. And then you can say, give me the next value of this iterator. The next is 1, 0, 1, 2, 3, 4. And then it will say stop iteration. So when the Python catches stop iteration, that's how it knows how to stop the for loop. And if you call it some more, it will also say stop iteration. But yeah, this is all the things you need to do to iterate in Python. But obviously, how do you compile it? How does it look in the bytecode? So obviously, you load the name, load the constant, you call the range of 5, and then you do get iter. Get iter is the same thing that the iter function I showed you. And then you say, okay, for iter. This is a thing that helps you iterate, It essentially is the loop. It is this part, that says like, if it's this, do that, otherwise do this, right? And you just say, for iter, you can either jump to the end of for if the loop has ended, or continue to the body of the loop. So, store name, you print the I, and then you jump backwards. Yeah. So, but okay, it's kind of complicated. How can you do that? Well, for now, I decided to do it like this. We have a range structure. Let me show it to you. Range, built-in range. Here's a function built-in range, which creates this structure, range iter. It has a current position, stop in the step. I just allocate it on the iter stack. So I have a stack of objects to iterate, and I don't have to allocate it in general memory, which I don't really have much of control of. But in the iteration, when you go into the next loop, you will always, it's like, you cannot, this iteration, okay, let me show you what you're trying to say, because I feel like I'm making it a little too complicated. So for example, I want to support not just this, but for j in range 10, and then we have something else, like for it in object, I don't know, like a map, or I, then j, and then like items or whatever. I want to support several levels of iteration. So when this level is finished, So like, for example, here I create the first iterator, here I create the second iterator, but here I will be creating second iterator every time. So for every I will create a new range here. You see how much it's not like, for example, it's like it's a big problem. Every time I get a new I need to create a new iterator, and I need to destroy the previous iterator. And every time I get a new j, I need to create a new iterator here and then destroy it. And if you just keep stacking them up, oh my, that would be an awful. So you will have 5 times, 10 times, whatever number here. It's a lot of iterators. So what I've decided to do is, hey, since this iterator will have to stay while we're iterating, but it will definitely have to go when the iteration ends. So I just have a stack of those. Whenever we enter new iterator, we push it to the stack. When we end the loop, we pop from the iterator stack. Yeah. So this way I don't have to manage, global memory. I don't have to allocate it on a heap. I have a separate just iter stack, and I just push and pop from it. Very simple. And all I do is, for the value, I just say it's a value of iter, and I just put the pointer as the thing. And when I'm trying to actually, for example, do the for iter, you can see, yeah, did I compile it? I didn't compile it. Let me show it to you. Let me show it how it compiles. Let's see. Obviously, it will print everything correctly. Yeah. And here you see how it's compiled. So I'm getting the value from the stack. I am casting the pointer to the range iter, and then I just do the execution of the loop. Yep. And you may think it's kind of, if you write a for loop in C, it will compile to a very, very simple thing, and it will be super fast. But if you compile this thing with what Python will do, so let's see, time of output dot out. Yeah, I mean, it jumps around, but it's like about, let's say 0.15 seconds ish. Let's see what about Python. Yeah, let's see. tst py. No, this is the wrong file. Yeah, let me literally copy paste whatever we have here. Yeah. Yep. Yeah. And it's consistently longer. It's consistently much longer. Like, I don't know, 0.5 seconds. And the previous was 0.1 seconds for our compiled bytecode. So dudes, why not, instead of doing just-in-time compilation on the interpreted languages, why don't we all the interpreted languages do the ahead-of-time compilation? It's like, it's not a very hard thing to transition, and even Python is doing the same thing, where they have a way to optimize the hot paths in the bytecode. So if you enable the speculative compiler, the Python will do just-in-time compilation of a hot path. It is not very popularly released yet, but it's like, why don't we do it ahead of time? Instead of while we're running the code, then we see the code is hot, and then we see, okay, let's compile it. It's just so crazy. We can literally copy-paste the whole thing. Since our code is here, it's not going to change. And I don't even want to... It's like the best thing is, it's a very simple compiler. It works very fast. And it hides your code. And I didn't implement imports yet. But when I will implement the imports, like, it just... You take all the modules you have and you compile them into one executable. Not a billion executables when you need to billion DLLs when you need to load the Python, the PyDLL and whatever. It's so crazy. You have just one executable. And if you really need to talk with the Python itself, you also statically link the Python runtime to your executable. So you have one executable, not a billion of them. Oh my. This is so fun. And obviously I've done some more fun stuff. So for example, I implemented functions. Yeah. Let me just show it to you. So I've implemented basic stuff, prints, inputs. You can have call an input and input something. You have a while loop. You have this stuff. You have some operations, ranges, modulos. Yeah, ranges with different number of arguments. So for example, obviously ranges with different numbers of arguments. How do you solve that? How do you do that? So all I'm doing is when I'm compiling, all the functions have the same arguments. First argument is number of Python arguments. Second is the array. So instead of passing here to this range, I'm passing one argument inside of an array, and here two arguments inside of an array. So when I implement this built-in range, it's very simple. Let me show it to you. Built-in range. All I'm saying is, depending on the number of arguments, if the number of arguments is 1, then this is the stop. So range of 5, we stop at 5. But we start at what? At 0. If the number of arguments is 2, we start from the first argument and end with this second argument. It's so simple. Yeah, I was thinking, in C you have variable number of arguments, and this is just the same thing, just more explicit. Yeah, very cool. What's next? Obviously, strings. You can check on strings and the functions. How to do functions? Let's see. Edit tst.py. How do you do functions? Well, let's see. Def hello. Let me just literally copy paste whatever is happening here. Yeah. Let's simplify it a bit. What do you think will be the disassembly of this thing? We have, okay, load const, code object. So here, Python says, okay, I have a load this constant, which is another compiled bytecode. So all Python is saying, hey, load this bytecode and execute it. And I'm like, okay, since I know this bytecode at compile time, the Python also gives it to me. Here you can see it. I can compile this bytecode first, and then I can compile here. And just here, instead of pushing something weird, I just use a function, push a function there. And let me show you what it compiles into. Yeah, I'm so excited because it's like I was to get even to this amount of things working in my previous attempt at compiling Python. I needed to spend like months or something because I was doing the work of the compilation of Python into bytecode. If you just take the bytecode and just super simply interpret it, like don't care about optimization, don't care about types. It's all good because the hardest thing in compiling Python is not making it faster, but even in just supporting the range of things, because you have all the modules, all the C extensions, and you also need to support them to have any real code working. So I was really hitting this bar hard because I was going hard on optimizing the output first without looking at the real code. Real code couldn't compile, but the fake math code could, and it compiled to very fast thing in sharp Python. But the real code didn't compile. Here I'm saying, don't care about optimizations. Even compiling Python to C is a very hard task in itself. If you can do this well, then you can optimize the output. So let's see what it compiles to. It's just, I was so in the wrong mindset of like, hey, like, I was still trying too hard to making optimizing compiler before making any compiler at all. Like, cause I couldn't compile most of real programs, then what the fuck is the point of this compiler? Okay, let's see. No. This. You know how the disassembly looks. Let's see what my compiler outputs for this thing. It's like, it's so crazy. I did it in just like one day or like one evening. Ha! I just love it. Hello there. Yeah. It makes sense. Let's look at how it looks. Output.c. Yeah. I have a global variable, which is a function. So you see the hello function is still a global variable. Then I have a real function in C that accepts argc argv. Then, since it doesn't have any arguments, it doesn't care about those things, but that's fine. You push the print, you call the print, and then you call the print, you call it. And here, when I am loading const, when the Python says load const code object, I'm literally just pushing a pointer to this function. Wow, it's so simple and it works. Wow, I just love it. I just love it so much. And obviously you can compile factorials as well, because like, since how can you access, so look here, for example, like you have a factorial function. How do you access this inner? How does it know about the outer? Because the outer is a global variable, it looks up, it sees nothing here, then it looks up at the global, it says, oh, there's a global variable, let's use it, right? And okay, one interesting thing I haven't actually tested is what about functions inside of functions? Yeah, it's very interesting. Let's see. Today is an exploration day as well. It's so cool. Let's see whether it will compile or not. So I have a function hello, and that's fine. But what if I wrap it into outer function, and then run the outer function? And it's like, obviously compiling to C is temporary. When I can have all the compilation to C done, I can transition to whatever backend, whatever optimizing backend I have. So you don't waste too much time concatenating strings, outputting the C code, and then making the C compiler reparse those strings. You can skip those two steps and directly say, hey, C compiler, here is the code, right? Whatever, the Clang, the LVM, MLIR, all those interesting things, it can come when this works with just C. Yeah, it's so cool. Okay, let's see obviously, what this will do in Python is just print hello world, because here you define a function, you run it, and here you also define a function and you run it. We can, let's see. It says hello there. What if I compile it? But actually, let's try first to disassemble it and see what it will look like. So what you have is load const, which is this thing, which is this, yeah. Then you make a function, you store it, then you push the arguments and you call it, yes. Here you also, so this is the global one, right? This is the global one. Here is the local one. Here you also obviously push the const, make a function, store fast. Right. When you have variables inside of the function, you have a fast variables, and instead here it will be stored to local variables of the outer function, the fast ones, and then called. Yeah, okay, sure, that is, yeah. And here I'll obviously do that. This definitely will compile. And will run. Yes, but what will happen if I say do a recursive call here? So if I is, I don't know, less than or equal to 0, then I just return, right? And here I call hello with I minus 1. And I can say hello there, I, right? And I say hello 5. It should print hello there 5 times. Disassemble tst. Yeah, it prints it 5 times. Then let's look at the disassembly. So, yeah, obviously it's not very interesting to see what's the outer. We already saw that. The inner, it has a closure. So here, hello says, okay, look at the local variables of the outer scope. And since we're using a variable from the outer scope, we will have a closure and we will have to capture it. I'm not sure if I have implemented the capture. Yeah, load closure. So my compiler will not compile it because I have not implemented closures, or how do you say that? Yeah. That's weird. Because I didn't copy paste it. Let's... Yeah, probably... well, okay. Yeah. So what I'm saying is, hey, make cell and make closure. So lambdas, essentially what this thing is doing is it's capturing a variable from the outer scope, which what lambdas do. So I have not implemented lambdas, so it doesn't work, but I don't think it's very hard to implement. You know, I will return to you in the next episode already probably implemented lambdas and importing, because man, it's so easy. It's so easy. How can I not do that? And I can also, it's like if you have a script that compiles your Python program to something you can embed to C. It doesn't really matter if it's sped up, but it's still sped up. It just have to work and you can easily embed it. It's so much powerful, you know, because usually you have to compile it to something that uses the Python, operations, the CPython library, and it takes lots of times to compile, and then you need to have a lot of DLLs. It's just so not good. If you have something simple and fast that can compile your Python code to C, your correct Python code to C, right? So here I'm saying that some operations may not make sense in Python, but if your Python code works and you compile it with my own compiler, then it will work and it will work faster. Yeah, Alright, that's my update to you for today. It's just like, hey, go ahead and implement your own little bytecode compiler. For example, you can go ahead and maybe implement a compiler for Java bytecode or something else. You know, there are a lot of interpreted languages. Not sure if JavaScript has a bytecode. What does V8 do? I know it has some... Like, look, you know, choose your favorite language, and there are probably even C interpreters, and look at ways to, instead of having a virtual machine, compile the bytecode into assembly, into C code. Yeah, and it's not optimized at all, and it's still faster. I don't know. I just love it. All right. If you want to know more about those types of things, about compilation, about parsers, about C, C++, and also optimizations, check out the top link in the description, because I teach this as well. I'm so passionate about. I think it's so important to have more people working on compilers and on tools for developers, because this is, you know, you remember the meme where you have a whole stack of things in our software, and it's holding by a little thing, and this little thing is compilers. No software can run if there's no compiler for the hardware. So go ahead, learn more about hardware, click the top link in the description, and have a great day.